I will show you some results of my experiments with implementing traffic simulation on a really large scale system. This is one of our focuses of research. We focus on computing and on using large scale computing systems in different ways, and actually we are more and more interested in applying functional technologies and languages in these applications, because they help. They solve lots of issues when it comes to using supercomputers. So these are the results I managed to collect using Erlang on our supercomputer in Krakow. We are working on microscale traffic simulation, on traffic simulation in general, on drivers modeling, on quite a few problems related to this subject. We have some novel ideas in this area which encourage us to go deeper into large-scale simulations and more detailed models which require high performance. So I will just briefly describe the background and then the implementation, the results, which are probably most interesting of it all. So the traffic simulation has been there for decades now, probably 4 or 5 or even more, using computers, of course. It all started on a very high level of abstractions when streets and cars were not very precisely represented. It was more like gas modeling or pressure modeling to just get some insights into the whole road system, how it may work. But from more recent research on the behaviors of drivers in especially city traffic, we can figure out that it just doesn't work that way. That if we use very simple models, if we use average models, it just doesn't give us the whole picture, and that individual drivers actually are crucial for the results of performance of throughput of city road systems. So actually one of our PhD students made experiments using a real car, and the real people, at least 15 drivers, drove the same route in Krakow, and he collected some interesting data where he shows that the differences between the behavior of a particular driver in the same situation can be very different between one and another, and it is a significant difference. This is actually a chart of braking before a crossroads, a distance on a horizontal axis and a velocity depending on the distance. So if we take an average model, it just doesn't reflect what really can happen in particular cases. So we want individual behaviors, we want precise models of cars, we want more and more details. But still, we need to have a simulation of a whole city. We don't want only one crossroad with a high accuracy. And we want the results as soon as possible, because we probably want to use this for forecasting some disasters, forecasting traffic jams, predicting what will happen in a few minutes, and maybe avoiding some unwanted situations. So if we want these three together, then we need truly high-performance computing to get it. And actually, my interest in it was how hard can it be? I'm a great fan of Erlang virtual machine, of its distribution mechanisms, and I wanted to try it myself. If it's really so hard to use Erlang on a supercomputer. So basically, the model I was using is a well-known and well-established discrete model of traffic by Nagel-Schreckenberg. It's been there for 30 years probably right now. This is a model based on a cellular automata where where space and time are discretized as well as velocity. So we have a street represented as a list of cells, actually several lists of cells which represent different lanes, and cell can be occupied or free, and each car has its velocity, and the direction is of course determined by the model of the street. Each car can accelerate, the acceleration is limited, but the deceleration is unlimited. So cars can stop immediately, which makes it quite simple to implement because you don't have to predict that you will have to stop in the future. So you simply, if there is no room for a car, it stops, and that's how the model works. So this is just a transition between two moments in time. So the yellow or greenish car had to slow down because it needs to reduce the velocity. It does it just instantly without any limitations. This basic model has to be extended because, of course, this doesn't reflect interesting situations which can occur in an urban environment. So I added lane changes. I added crossroads actually with traffic lights. So or with some traffic rules, like a right-hand rule. And I need to, well, take care of cars occupying the crossroads so that there's only one car in each cell every moment, even though a cell can belong to two lanes, two crossing lanes. And of course individual features, so each car may have a different acceleration and a different actually random factor, because there is also a random factor of slowing down spontaneously considered in this model. So now if we have this model, it's very easy to update it as a cellular automata. Just cell after cell, we consider if there is a car, if the cell is occupied, then we look at the velocity. We look in front, move the car to the proper cell, adjust its velocity, and that's fine. And we can do it for as big model as we want, unless we want to do it really fast. If we want to do it fast, then we need to split the model and do it in parallel. So now, how to update this model in parallel, and is it possible, actually? This is a good question, because the intuition just would say that it's straightforward. Let's just cut this city or whatever it is into pieces, and let's compute each piece separately, and let's exchange information about cars that are leaving and are incoming after each time step. This is a quite nice problem for parallelization, because the communication over here occurs only very locally. So each cell can be computed separately, not cell, each space as I call them, and they only communicate with several other spaces. This can be represented as processes or actors or whatever. So the communication is very local, and there is no centralization in this model. If we don't want to collect some statistical results or an image of a whole city in a particular moment, because we are, for instance, not interested in the whole picture, we can let it go. It can just run on this parallel machine, and we can look into particular spaces in particular moments to see if something's happening, or just put some breakpoints in interesting situations so that we collect some data and analyze it later. But it turns out that this method of parallelization is not as straightforward as we might think. Because if we have this update function which converts a previous state of this space into a next state of this space, it needs the knowledge about the incoming cars from other spaces, and this knowledge is a result of update of the other space. So actually this leads to a deadlock. So this can't be done. This cannot be done accurately because of these mutual dependencies. So each space depends on the information from a neighbor space, and it needs it before starting the update, which is impossible. So in this case, we have to accept some small violations of this general simulation rules of this simulation model. Which leads us to a little simplified equation where the state of one space depends only on a previous state of this space and previous states of the neighbor spaces. So we accept that the information needed on a border will arrive a little late, and we will incorporate it later on. This leads to a very small issues on these borders, but it turns out that they are kind of acceptable. What I tried to find out is it possible, if we accept one step, and we can kind of accept the errors or even remove the errors in such case, is it possible to go a little further? To accept a desynchronization between these spaces which exceeds this one step. So we simply accept n or d steps of desynchronization between these spaces. So it turns out that it is possible with one important factor in mind. So we can calculate the state without the knowledge about incoming cars, because the cars will just move forward, they will never move back. We can accept it as long as these cars do not hit any crossroad in this area. So we can accept this desynchronization level as d times maximum velocity. This is the distance between the entrance to the space and the first crossroad. This is what we can accept as a delay. And then we need to block lane changes on this small area, because how it's working. Each space publishes information that, okay, I have 10 free spaces on this road. So the neighbor space knows that in a time t, it can publish 10 or send out 10 cars to a neighbor. In t plus 1, at least 10. In t plus 100, at least 10 as well, unless it sent some cars before. If there were 10 free spaces, they won't disappear because cars don't move back, right? But if a car changes lanes, then it can block free space on a lane in front of it. So this led to actually violations of the model. So I had to block this small feature. Okay, so having this this model with desynchronization, I just prepared an implementation in Erlang. It was quite a nice experience, quite a short code, although it's data intensive. So I implemented all the model in maps, which kind of, well, no, they really work since Erlang 18. This version of Erlang is already available in our supercomputing center, so it's worked really nice. And this whole updating was like 400 lines of code, which is probably too many. I will probably be able to reduce it a little bit. But what was really nice and what was really interesting was how it works in distributed and parallel environments. So each process, each crossroad was executed in a single Erlang process, and each of these processes just communicated using the native Erlang communication between processes. And I used normal distributed Erlang without any messaging or other libraries or tools, just a distributed Erlang, but using hidden nodes only. So I didn't allow Erlang to build a whole graph of communication, which is not necessary here. The processes communicate only with a fixed number of different processes. So these connections were established, but there was no full network of connections between Erlang virtual machines. There were quite a few nodes, up to 800 actually. So I didn't want it to have such a huge network of connections, because there were at least a few reports that it just breaks quite soon. This distribution and this communication was all like 100 lines of code in Erlang, so it's quite nice. Now this is our little computer here in Krakow. It's called Prometheus. It's still on top 500, actually 53rd this year. It has 41,000 cores and something a little, 216 terabytes of RAM. I hope to use it all, but it's unfortunately impossible. They have like 30% of broken nodes on average. That's normal, so they just bring new and take some to for replacements. And also this cluster is split into 4 pieces because of some network issues, and getting access to more than 500 something nodes requires administration to work. So the experiments were tricky with bigger configurations. Okay, so the results. This is probably quite interesting. Starting from a single node with a growing task size, these are the results of the performance with increasing number of spaces per core. So if there were, actually each space had from 600 to 200 to 2,400 cells, and with a growing number of cells per core, which means that more processes were executed by a single scheduler, it turns out that the performance doesn't drop that badly. So this context switching doesn't take much effort. Actually, if there was a 1 space per core, which should be a perfect situation, turns out it is not, because the number of computation in different spaces will differ depending on the number of cars there are to process. So not actually in none of the cases this is the best performance situation. The best performance was when the number of spaces per core was between 4 and 8. This is actually the number of processes per scheduler. So between 4 and 8 is the best performance. Then it drops, and then it's just the error grows if the number is greater. But we can see that even if there are 256 processes per core, it's still quite holding the performance. So it's quite good. With a growing number of cores, we can see, well, the obvious case, if there are only 12 spaces, then adding more cores doesn't make much sense, so the performance drops. But in case of 48 spaces, the performance is pretty constant, so it scales really nicely with new cores, and this is still on a single node. So now the most important part. Yeah, 19,200 cores in total, and it scales. Yeah, it does. So these are the results for a performance of a task with 240,000 spaces and more than 11 million cars, and up to 19.2 thousand cores. In respect to, well, these are just the values, so the speed up in a moment. This is the zoom of this part of the chart. So as we can see, it grows, and it grows nicely. There is actually in this particular case there is almost no overhead on any kind of communication because it's only local. So this is the speed up chart. It's not as it's supposed to be presented because it's not in relation to a sequential version on a single core. This is compared to execution on 4 nodes, which is already 96 cores, up to 19,000 cores, and we can see that it's even super linear at the very end. This is actually because of the number of cores, the number of spaces per core. There were 200,000 processes to compute, and probably 19,000 of cores, which gives this optimal number of processes per core and the best performance for around 800 nodes running simultaneously. Okay, the desynchronization and the influence of desynchronization. This is very interesting. That it really matters, and it gives nice results, even more important than proper load balancing, we might say. I tested constant task size versus random task size. So the size of each crossroads differed within, well, the bigger one was 4 times the small one, and the size was random. So in case of random task size, of course, the performance of the whole system is a bit worse. This is actually on 100 nodes. But we can see that increasing the desynchronization, or actually introducing it, so going above the number of 1, can give better results than making sure that the tasks are on a constant size. So if we exceed the synchronization of 4, then the performance is above the performance in case of constant size and lack of the synchronization. This is probably quite interesting, but also predictable. What are the future steps? Well, for this work, for this paper that we are planning to publish, to compare it with sequential version and to compare it with implementation in different technology. Because obviously, okay, it scales, but Erlang is not designed for computing. This kind of computing, which is only an integers and not too demanding, is probably not that bad. But anyway, I would like to compare it with implementation in Java. Probably not in C, because I tend to think that it's not the point. So the Erlang is not there to overwhelm C in terms of performance on a single core. It's about the time of development. So it was like 3 or 4 days of work to get this running on a supercomputer. I can't even think how much time I would take to do it in C. Real-life scenarios, more precise models, and different problems. And these shells are not by accident. These are actually foraminiferas, which are small creatures, sea creatures, which indicate oil. So they are of great interest. There are billions of them in the oceans in particular parts of the world. And people want to know how they migrate and how they behave. So people want to simulate them. So this is the problem we are aiming at this scale. This is what we want to do next. All right, thank you very much.
So we have time for questions. Any questions from the audience?
Hi, I would like to ask if the purpose of the model is just to simulate the traffic, or if you are also trying to observe certain situations in the traffic, like traffic jams or something like that.
That's actually another next step I failed to mention. Obviously, we can do it. We have the whole road system. We need to make it more realistic, because right now it's just a synthetic bunch of identical crossroads. We have to load a real city, you might say, into this model. And then, of course, you are able to get the simulation results within a few seconds to see what will happen next. If you're able, for instance, to collect the data from a real city, load it into the system, then within 18 seconds we can get 1 hour of simulation of Manhattan. That's the scale. So you can predict and you can replan what to do next. Yes, we are planning to, this is one of the applications actually, to have it in real time, you might say.
I think now that everything's going to be autonomous vehicles, you can get the real driver now. You don't have to use psychology anymore. You can get the neural network that's doing the driving and put 1 million neural networks there and get what's really going to happen. And that'll be a real scenario.
Yes, we know that autonomous vehicles are almost there, and they also need planning in a whole city.
You have the real program. I don't need a brain person. Take that program.
Their behavior, yeah. And no one even knows how they will behave when there are 10 million of them in the real city. Yeah? So this is even more important.
Great, thank you. One final question.
Do you check how precise your prediction is?
Not at the moment. This is a whole domain of verifying the models. So collecting the data, simulating and comparing to reality. And actually this is only possible to have some statistical relevance between the model and the reality. We never tried it, but the model we are using is proved to not to be correct, but with proper parameters it can be correct. I mean relevant to reality.
Great. So thank you very much, Wojciech, for an interesting talk, and we look forward to chatting to you some more at the break. Thank you.